Hi, this is Stu Schwartz from MasterMathMentor.com. This is video Precalc02, and the topic is the trig functions. In this chapter, we discuss the basic trigonometric functions. We start with a right triangle. All right triangles have a hypotenuse, and we will look at one of the angles, which we will call theta. Relative to theta, we have the side opposite and the side adjacent, meaning next to. And they are on opposite sides of the right triangle. All triangles are created like this. So we have three sides: hypotenuse, opposite, and adjacent relative to theta. We now look at three trig functions, which will be a ratio of sides. So we start with sine theta, abbreviated SIN, and that will be the ratio of the opposite side to the hypotenuse. The cosine function, which is abbreviated COS, is the adjacent over the hypotenuse, and the tangent function, abbreviated TAN, is the opposite over the adjacent. We now have three other trig functions, which are the reciprocals of the first three. We start with the cosecant function, which is abbreviated CSC of theta, and that is equal to hypotenuse over opposite. We have the secant function, abbreviated SEC of theta, and that is the hypotenuse over the adjacent. And finally, the cotangent function, abbreviated COT of theta, and that is equal to the adjacent over the opposite. A good way to memorize this is with the term SOHCAHTOA. Sine goes with the opposite and hypotenuse. Cosine goes with the adjacent and the hypotenuse. And tangent goes with the opposite and adjacent. For the other three trig functions, it is a good way to remember this by knowing that S, sine, goes with cosecant, C. Cosine, C, goes with secant, S. And the other two uses the term tangent. Many times our angle theta is in standard position, meaning that its initial side is along the positive x-axis, and theta is developed from there. In that case, our sides can be labeled, instead of opposite, adjacent, and hypotenuse, as y, x, and r. And because of that, we then can redefine our trig functions in terms of the variables y, x, and r. So our trig functions are, first, sine theta, which we know is opposite over hypotenuse, or y over r. Our cosine function, which we know is adjacent over hypotenuse, and therefore cosine theta is equal to x over r. And our tangent function, which we know is opposite over adjacent, so tangent theta is equal to y over x. Our other three functions, sometimes called the cofunctions, are simply the reciprocals of our first three. So the cosecant function, cosecant theta, will equal r over y. The secant function, abbreviated SEC of theta, is r over x. And the cotangent function, abbreviated COT of theta, is equal to x over y. Because our figure is a right triangle, then the variables x, y, and r are tied together by the Pythagorean theorem. X squared plus y squared is equal to r squared. We will find that the Pythagorean theorem will be very, very helpful when we do problems. Please remember that there is no such thing as sine by itself. Sine doesn't exist by itself. It is sine theta or sine alpha, or if x is an angle, we would say sine x. But we never say just sine, as a trig function is a function of an angle. The angle must be present. It is like saying, take the square root. If I were to tell you, take the square root, you would most likely say, of what? The same is true with sine. We can't just take the sine. There has to be an of what, and that is the angle. No matter how you choose to do it, you must know the basic trig functions in terms of opposite, adjacent, hypotenuse, and x, y, and r, inside and out, backwards and forwards, and it must become part of you. If you were my students, I would be giving you quizzes every day for the immediate future to test whether you really know these definitions. You will find that if you learn them now, this course will be very, very easy. But if you just learn them and then immediately forget them, you're going to struggle throughout the course. So remember, memorize the basic trig functions. In problem 1, we are told that P is a point on the terminal side of theta that is in standard position, and we would like to find the 6 trig functions of theta. There are 6 points, and for each we would like to make a picture of the situation in order to find the 6 trig functions of theta. Since all 6 points are in the first quadrant, then the picture is the same for each. We have point P on the terminal side of theta, and from that we have a right triangle that is created with the x-axis, with sides x, y, and the hypotenuse being r, which is the square root of x squared plus y squared. In part A, our point is 3, 4. We know that the hypotenuse is 5, as the square root of 3 squared plus 4 squared is equal to 5. So sine theta is y over r, 4/5. Cosine theta is x over r, 3/5. And tangent theta is y over x, 4/3. Our cofunctions, cosecant theta is 5/4, secant theta is 5/3, and cotangent theta is 3/4. In part B, our point is 15, 8, and therefore the hypotenuse is 17. You should know the common right triangles with integer sides. 3, 4, 5, 5, 12, 13, 8, 15, 17, and 7, 24, 25, and their multiples show up all the time. So sine theta is y over r, 8 over 17. Cosine theta is x over r, 15 over 17. And tangent theta is y over x, 8 over 15. The cofunctions, cosecant theta is 17 over 8. Secant theta is 17 over 15. And cotangent theta is 15 over 8. In part C, our point is 5, 2. By the Pythagorean theorem, our hypotenuse is the square root of 29. Therefore, sine theta is 2 over the square root of 29. In this video series, we do not rationalize these fractions. It is simply easier to write 2 over the square root of 29 than 2 square root of 29 over 29. It will be, of course, up to your teacher the form that he or she prefers, but it is easier just to leave fractions with square roots in the denominator. So cosine theta is x over r, 5 over the square root of 29, and tangent theta is 2/5. Cosecant theta is the square root of 29 over 2. Secant theta is square root of 29 over 5, and therefore cotangent theta is 5/2. D has the point 1, 7. The hypotenuse is the square root of 1 squared plus 7 squared, which is the square root of 50. We will simplify the square roots and write the hypotenuse as 5 square root of 2. So sine theta is 7 over 5 square root of 2. Cosine theta is 1 over 5 square root of 2. And tangent theta is simply 7. Therefore, cosecant theta is 5 square root of 2 over 7. Secant theta is simply 5 square root of 2. And cotangent theta is 1/7. E is the point 1, 1. And the hypotenuse is the square root of 1 squared plus 1 squared, which is the square root of 2. So sine theta is written as 1 over the square root of 2. And in this case, we will rationalize, as this problem appears many times, and you should recognize that the sine theta of such a point is the square root of 2 over 2. The cosine theta is the same, square root of 2 over 2. Tangent theta is equal to 1. Cosecant theta will flip the sine theta, and the best way to flip it is simply to write it as the square root of 2, as is the secant theta. Cotangent theta is also 1. In F, our point is the square root of 2, square root of 7. And by the Pythagorean theorem, our hypotenuse is the square root of 2 squared plus the square root of 7 squared, which is the square root of 2 plus 7, or the square root of 9, which is 3. So sine theta is the square root of 7 over 3, cosine theta is the square root of 2 over 3, and tangent theta is the square root of 7 over the square root of 2, which is the square root of 7/2. And again, we will leave that answer. Cosecant theta, therefore, is 3 over the square root of 7. Secant theta is 3 over the square root of 2. And cotangent theta is the square root of 2/7. Again, for the cofunctions, we can rationalize all three of them, but we choose not to. So far, we have only examined trig functions in the first quadrant. Let us take a look at the entire Cartesian plane to determine the signs, S-I-G-N-S, of the trig functions in different quadrants. As we have seen in quadrant 1, x is positive, y is positive, and r is positive, which means in quadrant 1, all trig functions are positive. In quadrant 2, x is now negative, while y is positive and r is always positive. So while sine theta remains as positive over positive, which is a positive, cosine theta is a negative over positive, which is a negative, and tangent theta is positive over negative, which is a negative. Since the cofunctions, cosecant, secant, and cotangent, are reciprocals of the main three functions, sine, cosine, and tangent, their signs will be the same. So in quadrant 2 of the main three trig functions, the only trig function which is positive is sine theta. In quadrant 3, x is negative, y is negative, but r is still positive. That means that in quadrant 3, sine theta is negative, cosine theta is negative, but tangent theta is positive. And the same relationships will be true with the cofunctions. So the only trig function that is positive of the main three in quadrant 3 is the tangent function. In quadrant 4, x is positive, y is negative, and r is positive, meaning that sine theta is negative, but cosine theta is positive and tangent theta is negative. And the same relationship is true for the cofunctions. So in quadrant 4, the only trig function of the main three is cosine theta. Students should recall this information at a moment's notice. However, it is not necessary to memorize it in this form. A good way to remember this is the expression ASTC. A stands for all trig functions positive in the first quadrant. S stands for sine is positive in the second quadrant. T stands for tangent is positive in the third quadrant. And C stands for cosine is positive in the fourth quadrant. And of course, if sine is positive in the second quadrant, so is cosecant. In the third quadrant, tangent is positive, so cotangent is also positive. And in the fourth quadrant, cosine is positive, so therefore secant is positive. Teachers encourage students to memorize ASTC by using a mnemonic. Sometimes all students take calculus is used. Others may use the humorous Aunt Sally takes crack. However you choose to memorize it, you should always be able to determine the signs, S-I-G-N-S, of any trig function in any quadrant. When we draw pictures of trig functions in quadrants other than quadrant 1, the triangle is always drawn to the nearest x-axis. The angle inside the triangle will be called the reference angle. It is defined as the acute angle formed by the terminal side of theta and the horizontal axis, whether it is the positive horizontal axis or the negative horizontal axis. Shown are four possibilities for point P formed by the terminal side of angle theta in standard position. From each point, we draw a vertical line to the nearest x-axis and then draw the triangle. The x and y variables are simply the coordinates of your point P, with the hypotenuse r being the square root of x squared plus y squared. The reference angle in all four cases for angle theta is the angle created to the x-axis, which we will call alpha. Notice that only in quadrant 1 is angle theta equal to the reference angle alpha. In example 2, we have 4 points that are on the terminal side of theta. You are asked to draw a picture showing the reference angle and then find the 6 trig functions of theta. In A, we have the point -8, 6, which is in the second quadrant. And again, we can see the second quadrant picture. So x is -8, y is 6, and r is the square root of -8 squared plus 6 squared, which is 10. So when we find our trig function, sine theta is equal to 3/5 as we reduce the fraction. Cosine theta is -4/5, and tangent theta is equal to -3/4. And the cofunctions, cosecant theta is 5/3, secant theta is -5/4, cotangent theta is equal to -4/3. When we have fractions that are negative, the negative could be in front of the entire fraction in the numerator or in the denominator. In B, we have the point 7, -24, which is in the fourth quadrant. And as we use the Pythagorean theorem, we realize that this is a special right triangle with integer sides where r is 25. So sine theta is equal to negative 24 25ths, cosine theta is 7 25ths, and tangent theta is equal to negative 24 sevenths. For the cofunctions, cosecant theta is negative 25 24ths, secant theta is 25 sevenths, and cotangent theta is equal to negative 7 24ths. In C, we have the point negative 2, negative 2, and that puts us in the third quadrant. Therefore, r is the square root of negative 2 squared plus negative 2 squared, which is the square root of 8, which is 2 root 2. Sine theta, when we reduce our fraction, is negative square root of 2 over 2, as is cosine theta, the same thing. Tangent theta is equal to 1. Cosecant theta is equal to negative square root of 2, and secant theta is also negative square root of 2, while cotangent of theta is equal to 1. D is the point negative 1 square root of 3, which puts us back into the second quadrant. The hypotenuse is the square root of negative 1 squared plus the square root of 3 squared, which is the square root of 4 or 2. Therefore, sine theta is the square root of 3 over 2, while cosine theta is equal to negative 1/2, and tangent theta is equal to negative square root of 3. For the cofunctions, cosecant theta could be written as 2 over the square root of 3 or 2 root 3 over 3. Secant theta is equal to negative 2, and tangent theta could be written as negative 1 over the square root of 3 or negative square root of 3 over 3. In example 3, we are given information about one trig function, and we would like to find the others. It is suggested that we draw a picture to describe the situation. In A, we are told that sine theta is equal to 12 over 13, and theta is in quadrant 1. We would like to find cosine theta and tangent theta. We draw the picture somewhat to scale in the first quadrant, with the opposite side to theta as 12 and the hypotenuse equal to 13. We know that that will make the remaining side equal to 5, as it is a perfect 5, 12, 13 right triangle. And therefore cosine theta is equal to adjacent over hypotenuse, which is 5 over 13, and tangent theta is equal to opposite over adjacent, which is 12 over 5. In B, we are told that cosine theta is equal to 2/3, and theta is in quadrant 4, and we wish to find sine theta and tangent theta. Since theta is a quadrant 4 angle, we draw our picture with x equals 2 and r is equal to 3. The reference angle we call theta, or any variable we want. We use this acute angle to find trig functions of theta. By the Pythagorean theorem, y equals the square root of 5, but remember, since theta is a quadrant 4 angle, we must use y equals negative square root of 5. That gives sine theta equals negative square root of 5 over 3, and tangent theta equals negative square root of 5 over 2. In C, we are told that tangent theta is equal to 3, and theta is in quadrant 3, and we would like to find cosine theta and cosecant theta. Realize that in quadrant 3, both x and y are negative. So in this case, y is equal to negative 3, and x is equal to negative 1. That makes the hypotenuse the square root of 10, as the hypotenuse is always positive. So cosine theta is adjacent over hypotenuse, which is negative 1 over the square root of 10, or if you want, negative square root of 10 over 10. And cosecant theta is equal to hypotenuse over opposite, which is negative square root of 10 over 3. Notice again that Even though we say that x is -1 and y is -3, we really do not know that. It could be any multiple of -1 and -3, as long as opposite over adjacent is equal to 3. It is easiest to use the integer values -3 and -1. In D, we are told that cosecant theta is equal to 6/5, and we would like to find cosine theta and cotangent theta. Notice in this problem, we are not told the quadrant. Since we do not know the quadrant, but we know that cosecant is positive, that means that sine theta is also positive, and that occurs in the first quadrant and the second quadrant. So the hypotenuse will be 6, and the opposite will be 5, making the remaining side either positive square root of 11 or negative square root of 11. We really do not know, since we do not know the quadrant. So therefore, we say that cosine theta is equal to adjacent over the hypotenuse, which is plus or minus the square root 11 over 6, and cotangent theta is equal to adjacent over opposite, which is equal to plus or minus the square root of 11 over 5. Sometimes we are less concerned with the value of the trig function and more concerned with whether it is positive or negative. So in example 4, we are given some information, and we would like to know in what quadrant or quadrants is the information true. To do these problems, it is always best to keep in mind our mnemonic ASTC, which we know stands for all, sine, tangent, cosine, and represents the quadrants in which those trig functions are positive. In A, we would like to know in what quadrants are sine theta positive but cosine theta negative. Realize that since sine theta is positive, it must be in quadrant 1 or quadrant 2. Cosine theta is positive in 1 and 4, which means that cosine theta is negative in quadrants 2 and 3. So the only quadrants that they have in common is quadrant 2. Theta must be a quadrant 2 angle. In B, we would like to know in what quadrants are secant theta negative and cotangent theta negative. When we think secant theta being negative, we also think of cosine theta being negative. And cosine theta is negative, as we just saw, in quadrants 2 and quadrants 3. When we think of cotangent theta being negative, we think of tangent being negative. And since tangent theta is positive in quadrants 1 and 3, it is negative in quadrants 2 and 4. So again, the only quadrants that these two have in common is quadrant 2. In C, we would like to know in what quadrant is cosecant theta negative, but cosine theta positive. Cosecant theta is negative in the same quadrants that sine theta is negative. Sine theta is positive in quadrants 1 and 2, and therefore negative in quadrants 3 and 4. Cosine theta is positive in quadrants 1 and 4. So the only quadrants that these two have in common is quadrant 4. D asks for the quadrant where all trig functions are negative. We know that sine theta is positive in 1 and 2, making it negative in 3 and 4. We know that cosine theta is positive in 1 and 4, making it negative in 2 and 3. And we know that tangent theta is positive in 1 and 3, making it negative in 2 and 4. And there is no quadrant that all three statements have in common. Therefore, it is impossible for any value of theta to have all trig functions negative. Shown is a 110-degree angle in standard position. We see the initial side on the x-axis. We see the terminal side in quadrant 2. What we do not see is the actual rotation. We have no idea whether our angle was created clockwise or counterclockwise. We have no idea if, to create the 110 degrees, we went through 1 full rotation, 2 full rotations, or 100 full rotations. Just as we can tell the time of day by looking at the sun, what we cannot do is determine how much time has passed in terms of days when we look at 2 positions of the sun. So far, all our angles have been between 0 degrees and 360 degrees. What about angles outside that range? We will find that since 360 degrees, or 2 pi radians, represents 1 full rotation, that when we take a trig function of an angle greater than 360 degrees, or 2 pi radians, the reference angle is the same as the angle created when subtracted 360 degrees from the original angle. So we can make this claim. We can add or subtract any multiple of 360 degrees, or 2 pi radians, to any angle, and the trig functions of that angle remain the same. So, an angle theta is coterminal with another angle in the form of theta plus or minus 360 degrees n, or theta plus or minus 2 pi n if we are in radians, where n is an integer. And while an angle is not equal to an angle coterminal with it, any trig function of an angle and one coterminal to it are equal. So 400 degrees is coterminal with 40 degrees, as we simply subtract 360. That makes it a quadrant 1 angle where all trig functions are positive. So with 850 degrees, we subtract 360 degrees once, then 360 degrees again, getting 130 degrees, making it a quadrant 2 angle. And the only trig functions that are positive in quadrant 2 are sine and cosecant. For 1,275 degrees, we have to subtract 360 degrees 3 times, leaving us with 195 degrees. This is a quadrant 3 angle, and the only trig functions that are positive in quadrant 3 are tangent and cotangent. For 900 degrees, we subtract 360 degrees twice, leaving us with 180 degrees. And that's a quadrant angle. So the sine of 900 degrees is 0, as is the cotangent of 900 degrees. The cosine and secant of 900 degrees are both -1, and the cotangent of 900 degrees does not exist, as does the cosecant. For -231 degrees, we add 360 degrees, and we get 129 degrees as our coterminal angle. That is a quadrant 2 angle, and as we've seen in quadrant 2, the only trig functions that are positive are sine theta and cosecant theta. For -721 degrees, we add 360 degrees 3 times, leaving us with 359 degrees. That's a quadrant 4 angle, and the only trig function that is positive in quadrant 4 are cosine and secant theta. Sometimes our angle theta is in radians. So with 31 pi divided by 6, we have to subtract 2 pi twice to give us a number between 0 and 2 pi. we get 7 pi divided by 6, and that is a quadrant 3 angle, as it is slightly greater than pi. In quadrant 3, only tangent theta and cotangent theta is positive. Finally, for negative 11 pi divided by 2, we have to add 2 pi 3 times to get a value between 0 and 2 pi. In this case, we get exactly pi over 2, which is a quadrant angle, 90 degrees. And for 90 degrees, sine theta is 1, cosine theta is 0, tangent theta does not exist, while the cosecant theta is 1, secant theta does not exist, and cotangent theta is 0. We have talked about trig functions for angles in quadrants 1, 2, 3, and 4. But what about angles that lie directly on the axes? These are called quadrant angles, and we will now go through how to calculate trig functions of them. Note that for quadrant angles, there are no longer triangles to construct. So instead of using our trig definitions in terms of opposite, adjacent, and hypotenuse, we will now use our variables y, x, and r, where y represents the distance from the origin to a point we will choose on the quadrant angle. We start with 0 degrees, or 0 if our angle is measured in radians. We choose a point along 0 degrees, which will be a point in the form of A0, where A is a positive number. For convenience, we will choose the point 1, 0. So x is 1, y is 0, and r, which is the distance from the origin to the point, is a positive 1. Therefore, sine of 0 degrees, y over r, is 0. Cosine of 0 degrees, x over r, is 1. And tangent of 0 degrees, y over x, is 0. The cosecant of 0 degrees is r over y, 1 over 0, which does not exist. The secant of 0 degrees is r over x, 1 over 1, which is 1. And the cotangent of 0 degrees is x over y, 1 over 0, which does not exist. We next look at 90 degrees, or 90 degrees plus or minus any multiple of 360 degrees, which gives us the same terminal angle. If we're using radians, we use pi over 2. We choose a point along 90 degrees, which will be in the form of 0a, where a is a positive number. We will use the point 0, 1. That makes x is equal to 0, y is equal to 1, and r, again, the distance from the origin to the point, is 1. So sine of 90 degrees, y over r, is 1, while cosine of 90 degrees, is x over r, is 0. Tangent of 90 degrees, y over x, does not exist. Cosecant of 90 degrees, which is r over y, is 1, while secant of 90 degrees, y over x, 1 over 0, does not exist. And cotangent of 90 degrees, 0 over 1, is equal to 0. We next look at 180 degrees, or 180 degrees plus or minus any multiple of 360 degrees. If we are using radians, then our angle is pi. Our point now will be in the form of A0, where A is a negative number. We will use the point negative 1, 0 for convenience, making x equal negative 1, y equals 0, and r, again, being the distance from the origin to the point, and always positive, is 1. That makes sine of 180 degrees, y over r, or 0, cosine of 180 degrees x over r, which is -1, and tangent 180 degrees y over x, which is 0. Cosecant of 180 degrees, which is r over y, does not exist, while the secant of 180 degrees, r over x, is -1. The cotangent of 180 degrees, x over y, does not exist. Finally, we look at 270 degrees, or 270 degrees plus or minus any multiple of 360 degrees. If we are using radians, then our angle is 3 pi over 2. We choose a point along the negative y-axis, 0a, where a is negative. Our represented point here for convenience is 0, -1, making x equals 0, y equals -1, and r, again, the distance from the origin to the point, is always a positive number, in this case 1. So sine of 270 degrees, r over y, is -1, while cosine of 270 degrees, x over r, is 0. Tangent of 270 degrees, y over x, does not exist. Cosecant of 270 degrees is equal to r over y, which is -1, while secant of 270 degrees is r over x, and that does not exist. And the cotangent of 270 degrees, x over y, is 0. You do not need to memorize the trig functions of quadrant angles. However, you will use them so often that you will end up memorizing them, whether you want to or not, especially the sines, cosines, and tangents of the quadrant angles. However, you should be able to generate them with a quick picture at any time, as these will be used in computations quite a bit, as we will see on the next slide. In example 6, you are to calculate the values of the expressions that involve trig functions of quadrant angles. Resist the temptation to go back to previous slides to find these values. Rather, make a picture, determine x, y, and r, and evaluate the trig function. Also, if any of these expressions involve a value that does not exist, then the entire expression value does not exist. A reads 5 sine of 90 degrees minus 12 cosine squared of 180 degrees. This terminology is used quite a bit. Cosine squared of 180 degrees is just a shorthand to write cosine of 180 degrees squared. So we have 5 times the sine of 90, which is 1, minus 12 times the cosine of 180 degrees, which is -1, squared. This becomes 5 minus 12, or -7. In B, we have the fraction 6 tangent of 180 degrees plus 3 cosecant of 270 degrees, all over -2 secant of 0 degrees. Tangent of 180 degrees is 0, cosecant of 270 degrees is -1, and secant of 0 degrees is 1. So we have 6 times 0 plus 3 times -1, all over -2 times 1. Answer is 3/2. In C, we have the expression 4 sine of 90 degrees minus 2 cosine of 270 degrees minus 5, quantity squared. Sine of 90 degrees is 1, cosine of 270 degrees is 0, and therefore we have the expression 4 times 1 minus 2 times 0 minus 5, and that quantity is squared. This becomes 4 minus 5, or -1 squared, which is 1. D reads -6 sine pi over 2 minus 5 cotangent 450 degrees, all over 3 cosine squared 0 minus 3 cosine of 0, quantity squared. This problem mixes degrees and radians. Since there are no units on pi over 2 and 0, they are in radians. Pi over 2 radians is 90 degrees. 0 radians is 0 degrees. So we have negative 6 sine of 90 degrees, which is negative 6 times 1, minus 5 cotangent of 450 degrees. The angle coterminal to 450 degrees is 90 degrees, and the cotangent of 90 degrees is 0. The cosine of 0 is 1, so we have 3 times 1 squared minus the quantity 3 times 1 quantity squared. This becomes negative 6 upstairs over 3 minus 9, negative 6 over negative 6, and the answer to this problem, D, is 1. We normally think of domain of a function y equals f of x as the set of allowable x values and the range as the set of possible y values. Since theta is created with values of x and y, it can be confusing when discussing domain and range of trig functions. So, when finding the domain and range of a trig function f of theta, we will define the domain of the trig function f of theta as the allowable values of theta and range as the possible values of f of theta. Since we know that trig functions of angles coterminal to theta are equal to the trig functions of theta, we will restrict theta to angles between 0 degrees and 360 degrees, or in radians 0 to 2 pi. Let's start with sine theta, which is defined as y over r. For the domain, since r is never equal to 0, that means that theta can be any value, and therefore we can take the sine of any angle. For the range, realize that the denominator r must be greater than or equal to any value of y. So since the absolute value of y must be less than or equal to r, then we have a fraction with the larger number on the bottom. Therefore, sine theta must be a number between -1 and 1 inclusive. For cosine theta, the exact same relationship is true as was true with sine. Cosine theta is x over r, and again, since r does never equal to 0, then theta can take on any value. And since cosine theta being x over r, the larger number will always be on the bottom. That means that the absolute value of x must be less than or equal to r, and therefore cosine theta must be a value between -1 and 1 inclusive. Tangent theta is slightly different. We know that tangent theta equals y over x. So for the domain, theta can be any value where x does not equal 0, meaning 90 degrees and 270 degrees. But for the range, there is no restriction on the relative sizes of x and y, which means that tangent theta can take on any value between -infinity and infinity. Cosecant theta is defined as r over y, and therefore the domain can be any value of theta where y does not equal 0. That means that theta cannot equal 0 degrees and theta cannot equal 180 degrees. For the range, now the larger number is on top. So since r is greater than or equal to the absolute value of y, that means that cosecant theta must be either greater than 1 or less than or equal to -1. Secant theta is similar to cosecant theta. It is r over x. So the domain is any value theta where x does not equal 0. That means that theta cannot equal 90 degrees or 270 degrees. But similar to cosecant, for the range, r must be greater than or equal to the absolute value of x. The larger number is on top, and therefore secant theta must be greater than or equal to 1 or less than or equal to -1. Cotangent theta works exactly like tangent theta. Cotangent is x over y, and therefore theta can be any value where y does not equal 0, meaning that theta cannot equal 0 and theta cannot equal 180 degrees. However, there is no restriction on the relative sizes of x and y, so therefore cotangent theta can take on any value between -infinity and infinity. All of this can be summarized in the two charts shown on the screen. We are generally more concerned with sine, cosine, and tangent theta than the other trig functions. So please remember that you can take the sine or cosine of any angle, while for tangent it is restricted to angles that are not 90 degrees or 270 degrees, using radians, pi over 2, or 3 pi over 2. And for the range, for sine and cosine, note that you will always get answers between -1 and 1 inclusive, while for tangent, you can get any answer. Any number between -infinity and infinity is okay for taking the tangent of any value theta. There are two triangles in trig that show up all the time. The first is the 30, 60, 90 degree triangle, and in such a triangle the ratio of sides are 1 to the square root of 3 to 2. That means that you could think of the side opposite 30 as 1, and that would make the side opposite 60 the square root of 3, and therefore make the hypotenuse equal to 2. Now that's not to say that all 30, 60, 90 degree triangles have sides 1 square root of 3 over 2. But the ratio of sides is 1 to the square root of 3 over 2. So for instance, if we multiplied every side in this triangle shown by 5, then the sides would be 5, 5 root 3, and 10. If you divided each side by 2, then your sides would be 1/2, the square root of 3 over 2, and 1. The other triangle that shows up all the time is the 45, 45, 90 degree triangle. This is isosceles, and the ratio of sides is 1 to 1 to square root of 2. Again, that does not mean that the sides of a 45, 45, 90 degree triangle are always 1 to 1 square root of 2. It means that the ratio of sides are those numbers. So for instance, if you multiplied each side by 3, then the sides would be 3, 3, 3 root 2. Or if you multiplied each side by 4 root 2, then the sides would be 4 root 2, 4 root 2, 8. So while we do not actually know the sides of a right triangle with theta equal to 30 degrees or pi over 6 radians, we do know the ratio of sides, and that will allow us to find the trig functions. So the sine of 30 degrees or pi over 6 is 1/2, while the cosine of 30 degrees is square root of 3 over 2. The tangent of 30 degrees is 1 over the square root of 3 or the square root of 3 over 3. The cosecant of 30 degrees is 2, while the secant of 30 degrees is 2 over the square root of 3 or 2 root 3 over 3, and the cotangent of 30 degrees is simply the square root of 3. For 45 degrees or pi over 4 radians, the sine of 45 and the cosine of 45 degrees are the same, 1 over the square root of 2 or root 2 over 2. The tangent of 45 degrees is 1. The cosecant of 45 and secant of 45 are both the same, square root of 2, while the cotangent of 45 degrees is 1. For functions of 60 degrees, or pi over 3 radians, we do not have to redraw our picture. We can use the 60-degree angle at the top of the triangle and realize that sine theta is opposite over hypotenuse, or the square root of 3 over 2. Note we cannot use y over r, as that is only true when our angle is in standard position. 60 degrees is not in standard position. The same is true with finding the cosine. The cosine of 60 degrees will be adjacent over hypotenuse, or 1/2. And the tangent of 60 degrees will be opposite over adjacent, which is the square root of 3 over 1, or the square root of 3. Cosecant of 60 degrees is 2 root 3 over 3. Secant of 60 degrees is 2. And cotangent of 60 degrees is the square root of 3 over 3. A term that you will hear all the time in trig is the friendly angles. The friendly angles are angles that are any multiple of 30 degrees, 45 degrees, or 60 degrees. These angles crop up all the time. The reason that they are called the friendly angles is that we can easily find the trig functions of each of them. What you see is called a unit circle because its radius is 1 unit. Unit means 1. It is possible to find the coordinates of every point that is shown on this unit circle. For instance, let's concentrate on the 30-degree angle. If we were to draw a right triangle down to the x-axis with the hypotenuse along 30 degrees, we would have a 30, 60, 90-degree triangle. And since the hypotenuse is 1, then we know that the side opposite the 30 degrees must be half of that, or 1/2. So by the Pythagorean theorem, x squared plus 1/2 squared is equal to 1. And x would equal plus or minus the square root of 3 over 2, but since it's in the first quadrant, it is positive. Hence, the coordinate is the square root of 3 over 2, 1/2. Let's do another one, this time 225 degrees. We draw this angle in the third quadrant and realize that the reference angle is 45 degrees. Setting up our 45, 45, 90 triangle, we know that x squared plus y squared is equal to 1, but in a 45, 45, 90 triangle, y is equal to x. So we have 2x squared is equal to 1, meaning that x is equal to plus or minus the square root of 1/2. And realize that we're in the third quadrant, x is negative, so therefore x is equal to negative square root of 2 over 2, and the point is negative square root of 2 over 2, negative square root of 2 over 2. Here are all the points on the unit circle for the friendly angles. Notice that in quadrant 2, the x is negative. In quadrant 3, both x and y are negative. And in quadrant 4, the y coordinate is negative. We could use these coordinates then to find the trig functions of angles. However, we will find that there's a slightly easier procedure which we will outline on the next slide. Rather than use the coordinates of the unit circle that we just developed, there's a much easier way to find the trig functions of friendly angles. First, you will draw the angle in the appropriate quadrant. From there, you find the reference angle, which we know is the angle to the nearest x-axis. This will always be 30 degrees, 45 degrees, or 60 degrees. We then draw the right triangle to the x-axis using that reference angle. Next, we find the lengths of the sides of the triangle with the special angle, making sure to include sines because of the quadrant. That means that the lengths of our sides will either be plus or minus 1, plus or minus square root of 3, 2, if it's a 30, 60, 90 degree triangle, or plus or minus 1, plus or minus 1, square root of 2, if it's a 45, 45, 90 triangle. And from there, we simply find the appropriate trig function. In your manual, you have a table showing the special angles in quadrants 2, 3, and 4. Let us show how all the values are arrived at using the technique we just outlined. We start with 120 degrees. To change to radians, we multiply by 2 pi over 360 degrees, and we get 2 pi over 3 radians. Drawing the picture, we see that our reference angle is 60 degrees. So we have a 30, 60, 90 degree triangle. Opposite the 30 is 1, but remember that the x is negative. The side opposite the 60 degrees is the square root of 3, and the hypotenuse is 2. Therefore, sine theta is square root of 3 over 2. Cosine of 120 degrees is negative 1/2. Tangent of 120 degrees is negative square root of 3. And the cosecant function, secant function, and cotangent function of 120 degrees is simply the reciprocal of the sine function, cosine function, and tangent function, respectively. We next move to 135 degrees, which is in the second quadrant. Multiplying by 2 pi radians over 360 degrees, this angle is 3 pi over 4 radians. The reference angle made with the x-axis is 45 degrees, and we have a 45, 45, 90 degree triangle. The x is negative 1 as we're in the second quadrant, but y is 1, and the hypotenuse is the square root of 2. So sine of 135 degrees is the square root of 2 over 2, while cosine of 135 is negative square root of 2 over 2, and tangent of 135 degrees is negative 1. The cosecant, secant, and cotangent functions are simply the reciprocals of the sine function, cosine function, and tangent function. For 150 degrees, again, the radian measure, we multiply 150 by 2 pi over 360 degrees, getting 5 pi over 6. The reference angle is 30 degrees, so we have a 30, 60, 90 degree triangle with the x being opposite the 60 degrees and being negative square root of 3, while the y is 1, opposite the 30 degrees, and the hypotenuse is 2. So sine of 150 degrees is 1/2, cosine of 150 degrees is negative square root of 3 over 2, and tangent of 150 degrees is equal to negative 1 over the square root of 3, or negative root 3 over 3. Again, the cosecant, secant, and cotangent functions are simply the reciprocals of the sine, cosine, and tangent function. We now have 210 degrees, or in radians, 7 pi over 6. This is in the third quadrant, and our reference angle is 30 degrees, giving us a 30, 60, 90 degree triangle. And our sides are 1 to square root of 3 to 2 in that ratio, remembering that both x and y in this case are negative. And therefore sine of 210 degrees is negative 1/2, cosine of 210 is negative square root of 3 over 2, while tangent of a 210 degree angle is negative 1 over negative square root of 3, or root 3 over 3. And again, we can take the cosecant function, secant function, and cotangent function by taking the reciprocals of the sine function, cosine function, and tangent function. For 225 degrees, we multiply by 2 pi over 360 to get 5 pi over 4 radians. Drawing it, we see that this is a quadrant 3 angle, and our reference angle is 45 degrees. So we have a 45, 45, 90 degree triangle, making the sides negative 1, and the square root of 2. So the sine and cosine of 225 degrees are both negative square root of 2 over 2, while the tangent of 225 degrees is 1. The cosecant and secant are both negative square root of 2, and the cotangent of 225 is also 1. The pictures for 240 degrees, 300 degrees, 315 degrees, and 330 degrees are shown, and the table of values completed. Notice the sameness about the values of trig functions of friendly angles. They are all based on the reference angle that will create either a 30, 60, 90 degree triangle or a 45, 45, 90 degree triangle. That is why it is so important to know these triangles backwards and forwards. The most common mistake that students make is forgetting the signs. I recommend, when making your picture of the friendly angle and then determining the quadrant, before putting in the values of the sides of the triangles, to fill in x negative in quadrant 2, y negative in quadrant 4, and both negative in quadrant 3. If you fill in the signs first, you will never get a friendly angle incorrect because of sign. In exercise 8, you are to calculate the value of these expressions. They all involve trig functions of either special angles or quadrant angles. Again, resist the temptation to look at previous pages. Rather than for each problem involving a special angle or quadrant angle, make an appropriate picture, calculate x, y, and r, and then find the value of the trig function. In A, we have 8 sine 30 degrees minus 6 cosine 60 degrees. Sine 30 is 1/2, cosine 60 is 1/2. Each of them are in the first quadrant, so we have 8 times 1/2 minus 6 times 1/2, 4 minus 3, which is 1. In B, we have negative 2 tangent squared 150 degrees plus 4 cotangent squared of 300 degrees. Tangent squared of 150 is the tangent of 150 degrees squared. So we have negative 2 times negative square root of 3 over 3 squared plus 4, and we have cotangent squared of 300 degrees, which is cotangent of 300 degrees squared, which is also negative square root of 3 over 3 squared. So we have negative 2/3 plus 4/3. Answer is 2/3. In C, we have sine squared of 350 degrees plus cosine squared of 350 degrees. Sine of 315 degrees is negative square root of 2 over 2, and cosine of 350 degrees is positive square root of 2 over 2. So we have negative square root of 2 over 2 squared plus square root of 2 over 2 squared. Each of them is 1/2, and 1/2 plus 1/2 is 1. In D, we have 4 sine of 150 degrees plus cosine of 240 degrees, and that quantity is squared. Sine of 150 degrees is 1/2. Cosine of 240 degrees is negative 1/2. So we have 4 times 1/2 minus 1/2, and that is 2 minus 1/2, or 3/2 squared, and answer is 9/4. In E, we have negative 5 sine 90 degrees minus 2 cosine of 120 degrees all over negative 5 sine 90 degrees plus 2 cosine of 120 degrees. Here we have a quadrant angle, and the sine of 90 degrees is 1, and the cosine of 120 degrees is negative 1/2. So we have negative 5 times 1 minus 2 times negative 1/2 over negative 5 times 1 plus 2 times negative 1/2. Doing the calculations, we get negative 5 plus 1 all over negative 5 minus 1. Final answer is 2/3. F reads, the quantity 2 cotangent 5 pi over 4 minus sine squared of 2 pi over 3 quantity squared. We generally think better in degrees than in radians. So we convert and get 2 cotangent of 225 degrees minus sine of 120 degrees squared quantity squared. Cotangent of 225 is 1. Sine of 120 degrees is square root of 3 over 2. So we have 2 times 1 minus the square root of 3 over 2 squared, quantity squared. This becomes 2 minus 3/4 quantity squared, which is 5/4 squared, or 25 over 16. In G, we need to calculate cosine of 300 degrees plus cosine of 225 degrees all over cosecant of 270 degrees minus secant of 150 degrees. Most of these calculations involve fractions, and we have 1/2 minus square root of 2 over 2 all over negative 1 plus 2 square root of 3 over 3. This is a complex fraction, and the best way to clear a complex fraction is multiply both numerator and denominator by the LCD of 2 and 3, which is 6. So multiplying by 6 over 6, we get 3 minus 3 square root of 2 over negative 6 plus 4 square root of 3. It is okay to leave this answer with the radical in the denominator. H asks us to show that the sine of quantity A minus B is equal to sine A cosine B minus cosine A sine B when A is 150 degrees and B is 240 degrees. So we need to show that sine of negative 90 degrees is the same as sine of 150 degrees, cosine of 240 degrees, minus cosine of 150 degrees and times sine of 240 degrees. To find the sine of negative 90 degrees, we add 360 to that to get to the sine of 270, which is negative 1. Sine of 150 degrees is 1/2, while cosine of 240 degrees is negative 1/2. Cosine of 150 degrees and sine of 240 degrees are both negative square root of 3 over 2. So we end up with negative 1/4 minus 3/4, which is negative 1. For I, we need to show that cosine of 2 theta is cosine squared theta minus sine squared theta for 3 different values of theta. For A, we have to show when theta is equal to 30 degrees that cosine of 60 degrees is cosine squared of 30 degrees minus sine squared of 30 degrees. Cosine of 60 degrees is 1/2. Cosine of 30 degrees is square root of 3 over 2, and sine of 30 degrees is 1/2. Square root of 3 over 2 quantity squared minus 1/2 squared is 3/4 minus 1/4, and that is also equal to 1/2. B is when theta equals pi over 6, so we have to show that cosine of 5 pi over 3 is cosine squared of 5 pi over 6 minus sine squared of 5 pi over 6. Again, it is best to work in degrees, so we need to show that cosine of 300 degrees is cosine squared of 150 degrees minus sine squared of 150 degrees. This is almost the same calculation as the one that we did in A, showing that 1/2 is negative square root of 3 over 2 squared minus 1/2 squared, and both give 1/2. In C, we need to show for theta equals 495 degrees that the cosine of 990 degrees is cosine squared of 495 degrees minus sine squared of 495 degrees. These angles are all too large, so we will find the coterminal angles, and therefore we need to show that cosine of 270 degrees is cosine squared of 135 degrees minus sine squared of 135 degrees. Cosine of 270 degrees is a quadrant angle and is 0. And cosine of 135 degrees is negative square root of 2 over 2, while the sine of 135 degrees is the square root of 2 over 2. When we square each of these and subtract, we get 1/4 minus 1/4, and that is equal to 0. For questions both H and I, we will find later that not only are these statements true for the angles given, but they are true for any angles, and these are called identities. This will be studied in further videos.